No, this is not. Ah, yes, that's the one that I wanted. Perfect. Now, in magnetostatics, we will start with the concept of the magnetic force. So before I continue, let me ask you, do you hear an echo?
No.
Okay. I'm asking because I hear my iPad cannot be muted totally. So I hear something small. It does not bother me at all. I don't hear it. Okay. Let's think about what we have learned so far in terms of forces. Okay, what we've learned so far is the following. Before we talk about magnetostatics, if you have a positive charge, and this is stationary, so it stays in the same place, then it radiates practically, it creates an electric field, but what we started with was not the electric field, but it was the electric force. So we said, if you have an initial charge like this, Q, and then you bring another charge near it, like this Q, this Q, then this green charge will feel a force. There is a force that is going to push it away. But if we had a different charge that was negative, this charge would feel the same force, assuming that the two charges were at the same distance from the Q, capital Q. It would feel a force that will pull it towards the positive charge. And we called this force the electric force. And we found that this electric force was Q times lowercase q 4 pi epsilon naught r squared, or let me r squared, where in this case, when we talked about this, r was nothing else but the distance between the two charges, r. And the direction of the force was along an unit vector that is shown here, all right? Shows the direction of the force. It's along the axis that connects the Q, the capital Q charge, with the other smaller charges, is along that line, and it's either forcing the small charge away or it's pulling it towards. So it's going to have either one of the two directions depending on the sign, on the polarity of the charge. All right. Now, what happens if this charge that we considered in electrostatics, and that was the basis of electrostatics. So that was the electrostatic force. Okay. Now, what happens if this charge Q that I have placed there, so let me just draw a line to make sure that it's a new topic. So this charge Q starts moving, and this charge is moving with a velocity v. All right, Q. Then what if I bring a charge here, a small charge, what did I have, like this, or green, this one, Q. What would this charge Q feel? What do you think? Can I
An,
hear?
an increase of force, depending on the distance between the two charges.
Yes, and what is this? Let me write here. So it's gonna feel an increase in the force, all right? So this is the distance r. And so this little charge, the green charge is gonna feel a new force, which is gonna be larger than the previous one, the electrostatic that it felt when the charge was stationary. But what makes it larger? What do you think?
The decrease in distance.
The distance is kind of, yes. That is related, that the decreasing distance is going to have an effect. But what else physically is going to be developed? This new, so how do you, okay, let me ask you then this. So I agree. So the changes in distance or the fact that the Q is moving is doing something, all right? It's not just the Q, it's not like, for example, let me ask you then this question. What if I had the following two situations? Okay, so I will make this smaller and let me add one more page here. And then I will have so one is moving with a constant velocity v. And in the other case, I will have the same thing. So in one case A is moving, v is constant. And in case B does not necessarily move, is not moving with a constant velocity, but is changing positions. So, for example, in B, it goes from point A, it goes along this line, and then goes, so it's stationary at A, and then it goes to B, and the B remains stationary in B for some time, and then it moves instantaneously to C, and then to D. So it goes from A to D, but not like with a constant velocity. It's just think of it as being at those multiple locations. So do you think that when we look at A, between the two situations, all right, so it goes and here moves from A to B to C and so forth, D. If we were to look between these two cases at points A, B, C, and D, would we see if in one case is moving with a constant V, in other cases just appearing in these two four locations, would we see the same force? What do you think?
Is the idea that the charge is appearing in these different locations that it's accelerating like infinitely?
No, they just appear. You know, let's assume it's like a movie that you have a charge, or maybe another way of saying it. Let's assume that you have a charge Q that is at A, and then you measure the force. Then you turn it off from A, you place it at B. You measure the force on Q, on the green Q. Then you move it at C, and then at C you measure, it's stationary at C, you measure the force. And then you move it at D, stationary at D, you measure the force. If the change in force was only due to the separate locations of the charge, then you would say that between moving along this, moving to these locations with a constant V and appearing at those locations would give you the same result. Do you agree? If I may if I articulated well? What do you think? Let me see what. Huh. So some people say here the following, that they're not going to be the same. The two cases where one is moving and the other just appears and stays, they are not identical. And why is that? Because when a charge is moving with a constant velocity, creates a different a physical effect. And the different physical effect is a different type of a force that is called the magnetic force. All right, so so F indeed, in this case, when the charge is moving with a constant velocity, F then is gonna be, of course, whatever F sub B you would have by the charge, all right, as it moves into the different locations. This is what we call instantaneously appearing, plus a new type of a force, which we call the magnetic force. And what is the new type of the force? So while in the first case in Fe is like QE, all right, that's how we derived, as a matter of fact, E, the electric field. In the second case, it's gonna be QV cross B. So now, as you can see, we have a new term. And this new term, oops, I did not mean to do that. This new term is from physics point of view, is a new thing. It's not like different manifestations of the first one. Is a new thing. So what we've learned so far is that when a charge is static and remains static, no matter where you find it, you only have one type of a field and maybe different values, depends on where the static charge is placed. And that is the electric field. But when it starts moving with a constant velocity, it creates a new kind of a force, which we call the magnetic force. And you can think from that, we define the magnetic field, all right? Because you remember what we said, forces exist, fields do not. So even if we eventually work with fields, fields are mathematical concepts. We introduce them to simplify things. So we get rid of the little charge Q, which is the observant. So the electric field does not have the impact of the observant, which is the little charge. That's where I am. I'm observing, I'm feeling these forces. But if you remove me from that, then you have an entity which is independent of the observant. So that's why we introduce E and we introduce B. Let me ask you now another question, which we are going to have to remember when we go a little later and talk about electromagnetic fields. So now we have two separate fields. They don't see each other. It's like one and the other. They don't see each other. They are invisible to each other. And we call them a static electric field and a static magnetic field. What happens if the charge V, if the charge Q, in this case, it's the small charge Q. What happens if this charge, or the original charge, all right, it starts moving with a velocity which is not constant, but has an acceleration? What do you think is going to happen?
Well, it should depend on how the acceleration is forming, because if it's positive or negative, the electric field force should be decreasing and the magnetic field force should be increasing if it's positive, and it should be the electric field force should be increasing, the magnetic field force should be decreasing if the acceleration is negative, right?
So that's good. And what then does that do as a result? It makes E and B interrelated. All right. So E and B do not change independently. They change in a way that is interrelated. And that's why we call that new field an electromagnetic field, because it has an electric and magnetic field that see each other. They are not invisible to each other anymore. So remember the following: a static charge creates only an electrostatic field. A moving charge with a constant velocity creates an electrostatic field and a magnetostatic field, and the two are invisible to the other. And a moving charge with a varying velocity, all right, it creates an electromagnetic field. So an electric and a magnetic, which are interrelated. So that's what you need to remember, all right, as we move forward. Okay, any questions so far with that introduction?
I actually had one question about the example that you just went over about the charge moving from point A, B, C, and D.
Yes.
I was a little bit confused by the way it was worded.
Yeah.
So it goes instantaneously from B to C. Does it stop at those points so that we can measure them, or is it?
Stops. So it's like, for example, assume that you have multiple charges, but only each situated at A. Let me try to articulate in a different way. Let's assume that you have 4 charges, Q, identical, one at A, one at B, C, and then the other at D. But every time you turn off all 3 of them and you keep only one on. So if, for example, the initial force only was doing the location of the charge, all right, and it would change because the location was changing, then you would need to have at every point on the green charge, the electric only force, and one will be the value depending on the distance of point A from Q, little q. At B will be an electric force due to the distance between B and little q, and then so on, between C and little q, D and little q, as every time you turn on only one charge. But when it's moving, and it's the same charge as the Q, the capital Q charge moving, and then it passes as it's moving through locations A, B, C, and D. In addition to the electric force that is going to create, which now that electric force is going to have the value that corresponds to that new distance, it's going to have also a new term, which is the magnetic force. That's what I wanted to say. Does that make it a little different, or is it easier to? Is it
A
better?
little bit.
Yeah.
So what you're saying is that if we ever had a problem and we wanted to find both the electric and magnetic field forces acting on a particle, just going across a wire, we didn't have any specific. I mean, we didn't have any different points. We just wanted to find out what it is with respect to a single point on that wire. We would first break it up, and then first find the electric field of a charge sitting at that point.
Yes.
And then
Yes.
the other case where there's a charge moving at that point, then sum them together.
Yes.
Okay. Thank you.
Exactly. Okay. So now, having said that, let us try to go from this equation, this relationship, which that's in fact what what we discussed was exactly this one. And now let's talk about not just a moving charge, but a current. All right, so current is a continuous flow. It's not just barely a movement of a charge. A current is a continuous flow of charges, and this flow is like going on a closed path. So even here, you see the example has a magnetic force on a current element. The current element is connected to 2 metals, and these 2 metals have to be connected. So the current cannot be ever developed on an open path. All right, the current needs to be on a closed path. Otherwise, there is no current. And the idea of a current is that you have a charge or a group of charges, excuse me, that are moving with the same constant velocity. And they are moving perpetually, all right, for an ideal case. They keep moving. In this case, if there is not one charge that is moving with the velocity, but it's a perpetual motion of a charge on a closed path, then the only thing you have in that case is only a magnetic field. All right, that's how now we leave the top equation that shows the two, both electric and magnetic, and we go to only the magnetic force, which is also what you see practically when the moving charge moves perpetually with the same velocity in a closed path. All right? So practically you can argue when you have a constant current, because that's what happens when a charge moves with a constant velocity v, you have a constant current. When you have a constant current, practically you cannot identify one single charge at any particular location. Do you understand a little bit that concept? It's like you cannot identify if you have an electron cloud. Now that we know more about atoms, most probably you have been told in physics that when you have an electron cloud, you cannot really, you know, what the energy that is on this cloud, you can compute the energy, but you cannot specify with accuracy the position of the electron. Do you remember that statement? That's the Heisenberg principle. Do you remember that? That you cannot specify the position of an electron and its energy accurately at the same time? That is what is, yes, people remember that from physics. So here, remember the following. The difference, there is a difference between a moving charge, Q, that I can see it moving. And usually moving charges, you know, when you have them, for example, if you have a particle that is charged and is moving, one particle moving inside moving with a constant velocity. People have that in accelerators where they can allow the single charge to move. And usually it's a particle, it's not an electron. But when you start having a constant current, you cannot specify the position, any position for the charge that created it, which are usually electrons. And that's why when you have a constant current, then you only have a magnetic field, practically. Even if we all know that a constant current is nothing else but electrons moving with a constant velocity. All right? So now, so you understand the concepts. It's very important to not get confused about this, put them into place compartments so you can understand how we move to one to the other, because that fundamental understanding is going to help you a lot later in everything you do. All right. Now, we are focusing, therefore, on the magnetic force. And what we say is the following. If we have a constant current, and this is, I will write it here, it's a current I. This current really is nothing else but E or Q, which is electron seriously, V. But because I cannot specify the position of the charge of the electron in that case that creates this current, then after I define it, and then from here go here and write this expression for the magnetic force, I don't talk about that Q anymore. I don't talk. I kind of forget this relationship. I forget it. Even if generated the concept of the current for me, I never introduce it again when I speak about magnetic fields. So since I cannot specify the location of the charge, what's the point of talking about this charge anymore? So now I'm talking about the magnetic field. And then what we say from here, from this previous relationship up here, we say that the magnetic force, which is this extra force that we feel from the moving charge, this magnetic force is nothing else but the cross product between, let me see here, between a current and the magnetic field that is introducing. All right. So let's look at this example. Here it says the following. Let us assume that we have two things. One magnetic field B that somehow has been introduced separately, all right, separately, and one current that it's a one wire that you see, and this wire has we find it in three specific situations. One that is neutral, there is no current that flows through. The other that carries a current, and the third that in the first one carries a current upwards, I mean from the bottom conductor to the upper, and the other that is in the opposite location and is asking to find out what the impact of this external B field is going to be on the wire. So what is happening? Obviously, the wire itself, when it does not carry anything, all right, it's neutral. You put that like neutral, inactive wire inside the magnetic field, nothing happens because there is nothing that goes through the wire. There are no charges. Second, when you start having moving charges, like in the second case, in case B, and those charges move upwards, for example, then these charges, they will create their own magnetic field, which interacts with the B field. So practically what you see is this force here that is exerted due to the constant B field, the green one, on the current that flows through the wire. And that's because the two magnetic fields, so the current itself creates a magnetic field that interacts with the other field because they happen to be along the same direction. And that creates a change of the condition of the wire, which we call a force. So you see that the wire is bending and is bending to one direction because of the presence of the B field. And if the direction of the current changes, the wire is bending in the other direction. All right, that is showing, is very similar to showing what happens to a charge, practically, a constant moving charge inside a magnetic field, because by itself generates a magnetic field inside another magnetic field. The two magnetic fields interact, and then they create this force on the wire in this particular case, which is stretchable, and that's why you see the wire moving to one or the other direction. Do you have any particular questions here? I want to pause a little bit because maybe conceptually you have some questions.
So even though a wire may be inside a magnetic or electric field, uh, does Gauss's law no longer apply then, because there would be an electric or magnetic field going through the wire around? Or does that make sense?
So you have a wire and then it's inside an electric field.
Right. And then the Gauss's law dictates that there will be no electric field within that wire. But due to the electric field acting upon that wire, would there then be electric field to consider? Or
So that's here the interesting thing that I wanted to tell you. On one end, if the wire is disconnected and it's a wire section, under the electric field, and depending, if you have an electric field, all right, if the wire is disconnected, is a piece of wire, and then it is inside an electric field. Depending on the direction of the electric field, yes, you may split the electrons from the positive nucleus, and you may have a dipole. So all of the electrons will go on the one edge, all of the nuclei will go on the other end, and then you create a dipole. This is like the form of an antenna, a receiving antenna. All right, so you put an antenna inside an electric field, it's going to receive something, obviously. But if the wire is connected, is in a closed path, is closing, say, then there is going to be in the electric field, you will never have a current of any form if it's an electric field, because even if they separate locally, they recombine. See what I'm saying? It's like if you have a perfect conductor, why do we not have an electric field inside a perfect conductor? Because you may have, when you have an external field, you may separate the charges, but eventually they recombine into zero because everything moves with the velocity of light there.
Okay. Thanks. That was a good explanation. Thank you.
Okay. All right. So now, since we define the magnetic field, we will try to, now we have the current, of course, in the closed path. And then there is this integral form of the magnetic force. But what I would like to do for you is to not start with this, but to introduce a couple of laws, like we have the Coulomb law. Now we have, so we'll have, like we have a duality kind of thing between electric and magnetic fields. So in electric fields, when we have a charge, and then we understand that there is a static charge, there is an electric field, then at some point of the electric field, we know what kind of force is going to apply on another charge that we bring in. Like a charge, for example, if I am an observer, I am on a charge. And then from that electric force, we find the electric field. You remember? And the electric field then is Coulomb's law, we call it. In a similar way, we are thinking about the magnetic field. The magnetic field is, as I said, is like another, similar to the electric field, is a mathematical entity. We create it so we can get rid of the charge somehow that is moving and that kind of thinking. And we try to find a magnetic field from what generates it, which is an electric current. What is an electric current? Is a moving charge. However, this moving charge is in a closed path. Even if we may consider only a section of the closed path, the path at some point closes. That's why you have a continuous movement, perpetual movement of the charge. In that case, the law we are going to use, which is similar, I mean, if you observe it, there is something very specific that is visible both in the Coulomb's law and then the Biot-Savart law, that as you move away from the generating charge or current, the value, the intensity of the respected magnetic field, if it's a current, changes as 1 over r squared. The 1 over r squared, you will see it both in Coulomb's law and in Biot-Savart law. So there is a similarity. We call that duality. They are not identical concepts, they are different, but there is some kind of similarity between the two. So the dual to Coulomb's law for magnetostatics is the Biot-Savart law. And as a matter of fact, here you get exactly the formula that gives you, if you have a continuous current, closed path, but you consider only a short version of this current over a short length, and this current, because it's constant is value, so the current di, practically, I would write it as I, because the value is constant, dl. All right? That's how I write it. So then we get an expression for a differential magnetic field that is due to the differential current, because practically this relationship here, I would start writing it as following. I would go here, and the first one, the first way that I would write it, it will be dH is nothing else but di cross a sub r over 4 pi r squared. That's how I would write it, okay? Where then di, this one, is here, and therefore you come out with Biot-Savart law, all right? Which in fact, you see it here in this, and this measure, the magnetic field, pay attention if you may, to the units is amps per meter. Like volts per meter is for the electric field, for the magnetic field is amps per meter. Okay, and that's how we define the magnetic field. So at some point, if I have a wire, at some point in space, I feel a magnetic field. So at this point here, I feel a magnetic field, which comes from this small section of the wire, of the electric current, di, and the direction is the cross product between the distance, the vector, along the line that connects the observation point P to the infinitesimally short current. So this R vector, cross product of this with the direction of the current, which is given by dl vector, divided by r squared, where r now here is the magnitude, all right? So r here is nothing else but the magnitude of this vector, all right? And because we know from the definition of a unit vector that this is nothing else but r over magnitude of r, then this one can be written as dh equals I over 4 pi dl cross r divided by r cubed, okay? Because of that relationship. And you may see it as 1 or you may see it as 2, that. Okay, any questions so far before I continue? Here, we introduced 2 different types of current densities, which is going to be extremely important. And then I will finish with Ampere's law. And then we'll continue from that next time. As with charge, where in charge we had how many charge densities? 3. We had the volume charge density, the surface charge density, and the line charge density. 3 charge densities for a charge. How many densities we have for a current? 2 only. Because the current does not have a line density. I mean, we call it current line, but it's not the same line density like the charge. Where along a line, you can divide the charge, a static charge, into smaller pieces. Along a line of a current, you cannot divide into smaller pieces. You may divide it for an integration, but each one of these small pieces is not called a current charge. The current is also a continuous line, all right? So whenever we define densities, the density is in terms of the whole one of these lines. So for example, you may, and then this is now what people are using as a standard. When we say line current density here, This implies how many of these lines I have per unit length. How many of the red lines of current I have per unit length. That is called a line current density. And a surface current density is this one. So this is line current density. And how do we measure it? In amps per unit length, all right? And this is a surface current density and is measured in amps per surface unit length. And from here, we're just gonna go to a new law, which is equivalent to Gauss's law for electrostatics that says the divergence of D equals Q. Here says the curl of H equals J. All right, so if there is a current density, J, that generates a magnetic field H, the relationship between the generating current and the resulting magnetic field is what is called the Ampere's law. And we're going to use it extensively next time. Okay, the last thing before you go, I will give you a quiz, which is this one. And I will, the only thing that I have to do is to change how much you're going to get, which is going to be 60 points. I will assign this quiz to you today, and you're going to have, it's going to be like on the, pay attention to this. This is going to be interesting. It's going to be very similar to the charge, to the static electric field when we had the coaxial cable with charge. This is going to be an equivalent of a coaxial cable, but instead of charge, which is static, we consider a current. And I would like you to think, I don't want to give you anything more than just we talked about the fundamentals. What I would like you to do is to think in terms of the fundamentals and find out, it asks the following. It says, the coaxial cable, now this instead of Q, we have a current. And it's time invariant current. What does that mean? That the current is like the result of a charge that is moving with a steady velocity. That's what it says. And then a ferromagnetic material is nothing else. Well, it's a material, all right? Consider it as a dielectric. And I want you to think of whether there is an electric field. In what region there is a non-zero electric field. That's what I want you to remember. You have a dielectric, which is a ferromagnetic, whatever, it's called dielectric. You have conductors. Conductors, the dark blue are conductors. And you have perfect conductors. And you have just a current that flows through the inside conductor. And obviously, you see that there's a current flowing through the outside conductor. So, considering that a current is nothing else but a charge moving with a velocity v, on the basis of what we said in electrostatics, qualitatively, I want you to tell me where you're going to have a magnetic field. Is that, I mean, I don't want you to know anything more, just the introduction of the magnetic field and whatever we talked about in charged coaxial cables. All right, so it's a very conceptual. I don't want you to think math, no math here, only the fundamentals. All right, and see what you do. Please do that. I will assign it 60 points, and please do it by Monday morning. Okay? Thank you.
Just to make sure, Professor,
Yes.
there wasn't any exercise assigned last time, right?
No, exactly. No exercise
you.
last time. Thank you. Thank you very much.